Hi everyone, I'm Karunj Irene from Group 48, and I'm going to take you through our project, which is a colorimetric machine learning architecture for non-invasive anemia detection through conjunctiva image analysis. Those are the keywords of our project, where we have anemia detection, colorimetric analysis, conjunctiva images, diagnostic imaging, hemoglobin levels, machine learning, non-invasive screening, and support vector machines. So our next slide has the presentation roadmap. We have data set overview, model overview, then the four models, then the model summary, the model limitations, the key takeaways, the next steps, and the references. So our data set overview, we have columns, and the columns we have numbers, the number of the patient, then the hemoglobin level, then the gender and the age. In the gender distribution, we have females and males only. Data set is mixed but slightly male heavy in it. Then age distribution, the range is from 19 to 88 years. Then the key observations from our data set, the low hemoglobin values are found mostly in females, especially older ones. Then the high hemoglobin values are found mostly in younger, middle-aged males. Then the normal range is common across both genders, especially in the middle-aged adults. So our model overview, I worked upon four models. We have the SVM, the random forest, the gradient boosting, and the lightweight CNN. So random forest and gradient boosting are under ensemble machine learning. Then the CVM is under classical machine learning, and then lightweight is under deep learning. So the modality of these, so SVM, random, and gradient boosting, they share the same modality because they use handcrafted features. And then the lightweight CNN, it uses the end-to-end image and no more feature extraction. Then my first model was support vector machine using baseline core model architecture. So this is the overall pipeline where we input the image, you pre-process it, then you feature extract it, then you feature vector construction, then SVM and output prediction. So this other side has the detailed architecture breakdown of the overall pipeline, where under input we find that's where we put the image that we are working on. Then the pre-processing, you image resize it, then you reduce the noise. Then for feature extraction, that's where we find the color features and the texture features. So how the SVM works, the support vector machine works by finding the best possible boundary that separates two classes, in this case, anemia and non-anemic patients. Instead of just drawing any boundary, SVM looks for one that creates the maximum margin, meaning the largest possible distance between the two classes. Um, the key idea The key idea is that not all data points are equally important. SVM focuses only on the points closest to the boundary. Then in this project, the data is not linearly separable. Then once the model is trained, it uses the decision function to classify new data points. When you input a new image, its features are extracted and passed into the model, which then determines on which side of the boundary the point lies and classifies it if it's anemic or non-anemic. So the SVM hyperparameters, we have three. We have C, that's the regularization parameter, and then the gamma and the kernel. So the C, it controls the trade-off between margin size and classification error. And then the gamma, it controls how far the influence of a data point extends. Then the kernel, it transforms data into higher dimensions to handle nonlinear patterns. So my second model is the random forest using ensemble model architecture. So it's overall pipeline. We have you input the image, you pre-process it, you feature extract it, feature vector construction, random forest model, and the majority voting, then also the final output. So how the random forest works? Random forest works by taking the extracted features from anemia dataset, specifically the lab color features and texture features, and using them as input to multiple decision trees. The model first creates several random subsets of the training data using bootstrapping, and each subset is used to train a separate decision tree. Then during training, each tree also considers a random selection of features at each split to ensure diversity. Then when a new image is input, its features are extracted and passed through all the trained trees. Each tree independently predicts whether the case is anemic or non-anemic, based on learned patterns such as color intensity and texture variation. Finally, the model combines all predictions using majority voting, and the class with the most votes is returned as the final result. Then my third model is gradient boosting. So its overall pipeline, you input the image, you pre-process it, you feature extract it, then feature vector construction, gradient boosting model, sequential tree learning, and final output. So how gradient boosting works? Gradient boosting works by building decision trees sequentially where each tree learns from the mistakes of the previous ones. The model starts with a simple initial prediction, then compares it with the actual labels to calculate the errors. Using your dataset, the model takes lab color features and texture features and trains the first tree to capture basic patterns like paleness. After that, it calculates the remaining errors, and the next tree is trained specifically to correct those errors, focusing on harder cases where anemia is not easily detected. So this process continues with each new tree improving the model by learning differences in color and texture that indicates anemia. All the trees are then combined to produce a final prediction that is more accurate. Then my fourth model is a custom lightweight CNN, and its overall pipeline, you input the image, you pre-process it, then convolution plus RELU, then polling, then feature maps, then fully connected layer, then the output. So how the custom lightweight works? The lightweight CNN works by automatically learning important features directly from medical images instead of relying on manually extracted features. When an image is input, it first goes through pre-processing, then passes through the convolution layers that scan the image to detect patterns such as edges, color variation, and texture. As the data moves deeper into the network, the model learns more complex features like paleness and texture differences, which are key indicators of anemia. So the RELU activation introduces non-linearity, allowing the model to capture complex patterns while pulling layers, reduce the image size, and focus on the most important information. The resulting feature maps and then the flattened into a vector and pass through a fully connected layer, where the model makes a final decision. A sigmoid activation is it to output a probability which is then classified as either anemic or non-anemic. That's the output. So the comparison between the models, as I had already said the other side, that the random forest and the gradient boosting are under ensemble learning, then SVM is under nonlinear, then lightweight is under deep learning. And then for feature handling, SVM, random forest, and gradient boosting, they use manual features. Then lightweight, it uses automatic feature learning. For it learns directly from images, then captures the complex pattern. Then the other three, they work well on small data, clear boundaries, and reduces overfitting and high accuracy. Then the limitation for SVM, it is sensitive to parameter tuning. Then random forest is less interpretable. Then gradient boosting is more complex. Lightweight needs more data and computation. So the model summary, SVM strength, it is simple, interpretable, good for separable data. Then random forest, it handles nonlinear patterns. Then gradient boosting is high accuracy, and then custom lightweight is best performance. As I was training my models, I looked at the accuracy as well. So the accuracy of SVM is 83%, then the random forest is 87%, then gradient boosting is 89%, and custom lightweight is 91%. So the key takeaways for the support vector machine, its best use case, because I already talked about the strength and the weaknesses in the previous slide. So I'm only going to talk about the best use case here. So for SVM, the best use case, we have quick baseline model to establish a benchmark. Then random forest is its best use case is balanced choice when you want strong performance without deep learning complexity. Then gradient boosting is when accuracy and precision are critical, especially in medical and diagnostic tasks. So the next steps, refine the data. You clean and normalize the data set, add more clinical features if available, and balance the classes to improve the model reliability. Then you also optimize the models, then evaluate with richer metrics, then you prepare for deployment. So these are some of the references that I was looking at as I was working on my models. They are 3. Yeah. So current hiring, thank you very much.